Okay, guys. Now I received several requests about the question related to finding a least order to a differential equation when the solution format is given. I actually made a small video about that, but I thought of giving it a more lengthier explanation. Now, before going through this current video, I highly recommend you to go over my class recording because all the related theory will be discussed in there. Okay, right. So for this purpose, we should first start with, let's have a look at the case where you have the order as 2. First of all, when it comes to the order of a differential equation, we are only talking about the cases where you have a constant coefficient. And if we have a differential equation with constant coefficient, we always convert it into a polynomial with the same degrees and with the same coefficients. So basically, the order of the differential equation is directly equal to the order of the polynomial that we are converting into. Therefore, to find the order of the differential equation, we mainly focus on the order of the polynomial, its corresponding polynomial. So, this entire question is reduced down to finding the order of that particular polynomial. And to find the order of a polynomial, if we know the number of roots of that particular polynomial, then that number of roots is equal to the order of the polynomial. There's something you should be careful about. That is, if you think about a polynomial like this, it has an order 2, but you can see that the root is just equal to 2. However, because of this squared sign, it actually has 2 roots, but the thing is both roots are equal. So still you have 2 roots, although it is the same number. So you have 2 roots, the order is 2. Okay, so although it has similar roots, or I mean equal roots, it still counts as 2 roots. Okay, so that's something you should understand at first. Right. Now, we mainly focus on finding the order of this polynomial. In other words, we focus on determining the number of roots. Okay, right. Now, if we think about the pattern of the solution with respect to the nature of the roots, if the order is 2, this is what we learned before. So when you have 2 distinct roots, you have this format, C1ER1T, C2ER2T, right? And what you should understand is, in this format, okay, when you have this format, they can give you some initial conditions to determine the values of these C1 and C2. And sometimes they can be 0. So, for example, we can have some initial condition where C1 is equal to 0. I'm talking about this case. And C2 is equal to 4.5. Then, in that case, our solution for that given differential equation with the given initial condition will be 0 plus 4.5 ER2T. That's it. Okay, so we will just have this term only in that case. Right. Now let's proceed. If we have complex roots, this is not real numbers, we have this form. Okay, those are the things that we learned before. And when you have equal roots, we have this. Now, the same format is followed even when you have n as the order of the polynomial. So, in other words, if we are talking about an nth degree differential equation or an nth degree polynomial, so this is the differential equation and this is the polynomial that we are referring to. Then still the nature of the solution will follow the exact same pattern. That is, if you have, let's say, a distinct n number of roots, you still write the same form. Okay, keep in mind that these constants can be zero. As I explained in my lecture, it can be zero. So I highly recommend you to go through the lecture video first before watching this current video. Okay, right. Now, and then the second point here is complex roots. And in the more generalized version also, if you have several complex roots, remember complex roots come as conjugate pairs. Okay, so if you have one, you definitely should have the other conjugate pair. That's a pattern we observe in polynomials and roots. Right. So now, if you have conjugate pairs, or I mean complex numbers, this is the way you write down the roots. You have, if you take this pair, you have lambda 1, mu 1, lambda 1, mu 1. The first one is with plus and the second one is with minus. So you get C1e lambda 1t cos mu 1t, e lambda 1t sin mu t. So we do not include this negative anywhere in the solution, right? So these two terms represent this pair. And similarly, we write for the other pairs as well. These two represent the other pair. Okay, right. Then this is the part where sometimes people get confused. Then this is the case where you have repeated roots. Now in my previous two examples, categories, I just used some general terms like R1, R2, R3, and Rn. Okay, but to explain the repeated roots, I am choosing some direct examples where I include values for these roots. So let's start with this first one. Suppose you have a repeated root which is equal to 4, and that's it. Okay, say you have a polynomial extracted from the differential equation, and in that polynomial the root is equal to 4, and that's it. And it should be repeated 3 times. So it's basically r equals to 4, r equals to 4, and r equals to 4. Something like this. R minus 4 cube is equal to 0. Okay. Right. Now, when you have something like that, it again follows the same pattern. Okay. So remember, when you have two repeated rows, you have one term without a t, and the other term will have a t term. And here, since you have three repeated rows, you get T0 for this one, T1 for this one, T2 for this one. That's the pattern we have. And you have to remember that. So then, now let me write another example. So suppose you have, let's say, where should I write? Let's take R1 equals to R2 equals to R3 equals to R4 equals to So then the solution will be C1E over 4E plus C2E 4E plus C3E squared E 4E plus C4 E cube E4T. So you have to have 4 terms altogether because of these 4 repeated roots. And here you have T0, T1, T2, and T3. That's the pattern we have. Now the thing is, when you have stuffs like this, with the initial conditions you have for the differential equation, sometimes these terms may vanish. For example, if you have C1 equals to C2 equals to 0, and let's say C3 equals to 2.2, then what remains is YT equals to 2.2 E squared E40, right? So this is the term that remains when you have this equals to 0, this equals to 0, and C3 is equal to 2.2. Okay, right. Now, we write that down. So, what we have is y equals to 2.2 e squared e 40. So, now suppose you only have this line. Let's think in the backward direction. If they just give you this term, okay, if they just give you this term, what should be the least degree? Now, in that case, what you should realize is, you should first figure out that you have a t squared term. How did you get the t squared term? You must have a repeated root where the remaining terms were written like this. And the third term will be this one. Okay. Therefore, as a result, you should have 3 repeated roots. In other words, our polynomial should have a degree 3. Now, how about this? Let me do this one. Okay. But how about this? What if we have something like this? Yt equals to, let's say 2.2 t times t4t. Now, earlier what I wrote was yt equals to 2.2 t squared e4t. That's what I wrote earlier. But now suppose you have something like this. Okay. Now, if you think about this equation, you can see that you obtain 2.2 by how? You obtain it by equating this to 0, this to 2.2, and this to 0, right? So if you want to think about the backward direction, while keeping this starting equation in mind, you might think that you should end up with the third order polynomial because we obtained this equation by using a third order polynomial, right? But within this equation, if we equate and if we define some initial conditions where you have C3 equals to 0, C1 equals to 0, and C2 equals to 2.2, then the end result that you get is this one. However, if you are going to start with this format, and if you are going to think backwards, and if you are trying to figure out the least order,
then there is no way to figure out this third term. That is the reason why they ask for the least order, because there can be some higher order polynomials as well, but we are interested in the least order. So if you want to find the least order, and if this is the expression you have, then what you should think is, now it starts with T. So to get a T, you should at least have two repeated terms. There is no way for you to confirm the existence of a third repeating root if you just have this term only. Okay, so it is possible to have three terms, and even if it is possible to have four or higher terms, but if at least you should have two terms. That's the whole point behind this calculation. And if you have this one, t squared, you should at least have three repeating terms, and there might be some higher order polynomials as well, but at least you should have three repeating terms, and you cannot have this solution format just by using two repeating roots. In other words, just by having a polynomial of degree 2, or in other words, just by having a differential equation of order 2, you will never be able to obtain this as a solution. And keep in mind that we are talking about constant coefficient homogeneous differential equations. Okay. And homogeneity is also important. We are talking about homogeneous equations, right? Okay. So, right. Now, I hope this part is clear to you, right? When you have something like this, we pick this number, and you can see that now this to get this solution, you should at least have a polynomial of order 3. Okay, next let's move to this one. So here we have three repeating roots of this degree, this value, and another root which is not repeating. In that case, these three terms corresponds to the repeating numbers, and this alone goes with this single root. Okay. Then again, just assume that you have set initial conditions so that this is 0, this is 0, and this is, let's say, 4.5, and this is 6.3. I'm just picking some random numbers. Then in that case, the solution that you're going to get will be 4.5 t squared e4 t plus 6.3 e5t. So now let's think backwards. If this is the solution that they have given, okay, if this is the solution that they have given, what should be the minimum order of the polynomial? Now for that, if you focus on this right-hand term, you can see that it's just 6.3, that's some arbitrary constant, times e to the power 5t. And this number 5 is not present anywhere else. So from that fact, you should be able to conclude that there is a single root which is equal to 5. Okay, so in our polynomial now, the whole purpose of this calculation is to determine the degree of the polynomial, right? And determining the degree of the polynomial means determining the number of roots. Okay, so basically we are going to determine the number of roots. So for this particular case, since we have 5, now we can safely say that we have the root is equal to 5. But that's not it. That's not the end. We also have this term. Right. Now, in this term, you can see that there's a t squared term, and the only way you can obtain a t squared term is by having at least 3 repeating roots. Remember, keep in mind that I'm using this word at least because it's important. The reason is you can even have a polynomial which is greater than 3, but you can never have a polynomial which is less than 3. So at least your polynomial should be having a degree of 3. So here you have 3 repeating roots, and to have a polynomial with 3 repeating roots, you should at least have its degree equal to 3. So from this you have 3 roots, and from this you have another root. So basically you have 4 roots. And here the repeating root, by looking at this number, you can say that the repeating root is 4, is repeated 3 times. So these will be the roots of our polynomial. For polynomial, therefore, this polynomial must be of degree 4, at least degree 4. The thing is, now you can, this might have had something like, let's say, C5t to the power 3e4t. However, this might be 0. So we don't know about anything about higher order terms, which will result in increasing the order of the polynomial. So we have to deal with the facts that we already have, right? So to have these results, you must at least have a polynomial of degree 4. Okay. Now, but however, you can even have something like a polynomial with degree, let's say 5, where the roots were r equals 5, r equals 4, r equals 4, r equals 4, and maybe r equals 4, another 4, and maybe some other number. Then y will be equal to C1e 5e plus C2e 4e plus C3e squared e 4e C4e cube E4e, one term, E5 E4e. So that's the place where you should start. And then C6 E10t. You can even have something like this. And then if you have set the initial conditions so that these are zeros, you can once again obtain this polynomial, right? You should set the initial conditions appropriately so that you have the required terms and other terms will vanish. Once again, you still can get this polynomial, and here in this case, the polynomial will have like 2, 3, 4, 5, 6. It will have a polynomial of degree 6, and then still you can get the same solution, right? However, you can never expect this solution with the polynomial of degree less than 4. So at least 4 should be there, and this number 4 was obtained by this method. And that's what we target. Okay, right. Okay. Now let's go to the other problem. Then, now from here onwards, I'm not going to stress on the word at least. Okay. Now every time I am finding the least degree, but keep in mind that there can be some higher degree polynomials as well. Okay. Right. Now let's focus on this one. So here we have two roots that are complex numbers and two repeated roots. So for the complex numbers, you can see that they are not repeated and you follow this format. That's the one I have taught before. And for the repeated roots, you have this form. Okay. Now, say you have a solution given as, let's say, 2 point e to t sine 3t and 5.6. I'm just picking some random numbers. E5t. Okay. Then what should happen? You should realize that if you think about this particular term, once you see a sine term or a cosine term, you should understand that it has come from a complex number. Okay? And to be specific, this term has come from the complex number 2 plus 3i or 2 minus 3i. Okay? So that's the only way you can expect a trigonometric term like this, right? And that means just by looking at this term, we can say that you have two roots, R1 and R2, and the cosine term, that is the kind of like, when you have complex numbers, the roots will always have these two pairs. However, at the end, if you only see a single sine term or a cosine term, that means the corresponding arbitrary constant for the other trigonometric term has become zero because of the initial conditions, right? That is why you are left with only this term. However, to get this term, you must have two more roots, right? So this term corresponds to two roots. And we can see this term. So here we can see the t term, and that means to get the t here, we should at least have two roots repeated. And by looking at this number 5, we can see that 5 is the repeated root and it has been repeated 2 times. So altogether we have 1 root, 2 root, 3 and 4. It has 4 roots, so the degree of the polynomial should be at least 4, right? Now suppose you have something like this, 2.2 e to t, let's say cos 3t, and 5.6 e 4 e 5t. How about this? In this case also, we can see that you only have a cosine term. However, that has happened because its sine term has become 0, has gone to 0 because of the arbitrary constant, right? Still, just by looking at this one, you have to figure out that you still, it relates to two roots. Let's say R1 equals to 2 plus 3i, R2 equals to 2 minus 3i. And how about this? Here you have 4. That means there should be 5 roots. 1, 2, 3, 4, and 5 roots. And that number should be equal to 5 because of this. So you have 5 roots, and here you have 7 roots. So altogether you should have, here you have 2 roots and 5 roots. Altogether you have to have at least order 5 polynomial. Okay? Right. And one more thing. Now, how about something like this? Say you have yt equals to 2.2 sine 3t and 5 times 60 in 5t. The only difference here in between this one and this one is you don't have this theta. What has happened there? Still, just by looking at the sine term, you can say that it corresponds to this sine and cosine term, which means that you have a complex root. However, this term is equal to 1. And the only way to make this 1 is by changing the real number in the complex root equals to 0. So basically, what you have is 0 plus 3, right? The other root is 0 minus 3. Those will be the two roots corresponding to this term. And for this term, since you have a t here, the root has been repeated 2 times. So we have r equals 5 and r equals 5. Once again, you have 4 as the minimum order of the polynomial. Right? Okay. Then, how about this one? Now here, you have complex roots that are repeated. Right? Now here, you have to be careful. Now for these two complex roots, you get this one. Right? That's the usual pattern. And since these are repeated, okay, you should follow the same pattern that we do for the repeated roots. It comes with the t. That's it, right? And everything else is the same. Okay? So now thinking backwards, imagine if we have something like this. Yt equals to, let's say, 2.2 t times e 2t sine 3t. So what will happen there? Now you should understand two things when you see a term like this. Now, because of this sine term, it is safe to assume that there is a complex root. So there is a complex root. That means you need to have at least two roots, R1 and R2, which are complex conjugates. And because of this term, we should realize that whatever the complex root we have here is repeated. Okay? So basically, we will be having a complex root which is repeated. So when you say complex root, from there itself you have 2. And by looking at this number t and its power 1, we can say that this whatever the complex root we have here has been repeated 2 times. So you get 4 roots for this one just by looking at this single expression 2.2 t into t sine 3t. We can safely say that you need to have a polynomial of order 4, at least order 4, right? And how about something like this? Yt equals to 2.2 t sine 3t. Here, once again, by looking at this sine term, we can say that there is a complex root. And by looking at this t term, we can say that there's a repeated root, repeated 2 times. I mean, repeated once. So, like something like this. And what has happened to this t term? In the complex number, the real part is 0. So, what you have is 0 plus 3i, 0 minus 3i, repeated again. That's 0 plus 3i, 0 minus 3i. Now, how about something like this? T equals to 2.2 t 5 sine 3t. Then again, this goes to two roots, r equals
R1 equals 0 plus 3i, R2 equals to 0 minus 3i. That's a complex number. Because of this, we can say that this was repeated 6 times. So 1, 2 times 6, you have to have a polynomial of order at least 12 to get this as a solution. We will never get this format as a solution for a differential equation with constant coefficient and variance and order less than 12. Okay? Right. Now, yeah, that's what I have done here. So when you have 3 roots repeated, you will get square here. And all the roots were repeated, right? Now, how about something like this? Now, combining everything together, what if I write something like, let's say, e to the power 5t plus t3 e to the power 6t, and then plus cos 5t plus sin 6t plus t squared sin 7t plus t squared plus 5t. Let's see, cos 8t, and then e cubed sin 10t plus e cubed cosine 10t. Okay, let's see. Here we have this term which goes with just the single root, right? So we have one root is equal to 5. And here we have another root which is equal to 6. And that root was repeated 3 times, 4 times. So you have 4 roots here. So here you have one root, and for this term it goes with 4 roots. And how about this? Now, you should not get confused with these two terms, okay? Because remember, when you have a complex root, okay? When you have a complex root, let's go to this part. So when you have a complex root, these two numbers, I mean, you should carefully understand how these two numbers go into the trigonometric terms. So here you have lambda, here you have lambda, and in both cosine and sine, you have the same mu. Okay, so if it is the same conjugate pair, if you have cos 5t here, you have to have sine 5t here. Now, if whatever the term you have here is different than this one, that means it represents a different conjugate pair. Okay? So, therefore, since the value in here is different to the value in here, we should get some complex number for this one and another complex number for this one. Basically, what you have is 0 plus 5i and 0 minus 5i corresponds to this coefficient, this term, that's 2 terms, and another one, 0 minus 6i, 0 plus 6i corresponds to this term. So that's 2 more. And then, how about this one? That's another complex root, right? So we have 0 plus
7i, 0 minus 7i, and it is repeated 3 times. So 2 rows repeated 3 times, you will have 6 rows. This is also the same. You have 6 rows. And finally, how about this one? Here also again you have to be careful because what you have is t3 times sine 10t plus cos 10t. So here this is the same thing. So what we can expect is the complex number which is equal to 0 plus 10i and 0 minus 10i, because these two terms are the same. If they were different, you have to handle them as two different roots. So we have two roots repeated 4 times. 4 times 2 is 8. So altogether, you have to add these terms 1 plus 4 plus 2 plus 2 plus 2, 6 plus 6 plus 8, and the result will be the minimum order of the polynomial that you should have, or in other words, the minimum order of the differential equation you should have in order to get this one as a solution. So I hope you have the better understanding about determining the least order. Just let me know if you still have any questions.